Today let's talk about scattering of electrons. Now, the general formalism for treating scattering is to consider this kind of a transition probability that you may have learned in your quantum mechanics. You consider the probability of an electron changing state from wave vector k to k prime under the influence of a perturbating Hamiltonian H prime. Now, if this perturbating Hamiltonian is independent of time, then one can show that the scattering is elastic, and when the perturbating Hamiltonian is dependent on time, then the scattering becomes inelastic. Now, in a solid, what are the sources of scattering for electrons? We saw that if I consider a static lattice, because the potential is periodic, the electronic wave functions can still be approximated as plane waves times some periodic function which obeys the periodicity of the lattice, and the velocity is basically a stationary state, which means that the velocity is independent of time. So the scattering originates from two sources. One, defects in the solid. Because there are defects, then the periodicity will be broken, and that will naturally result in the electron getting deviated when it hits that hits that defect or passes close to the defect. That's one source, and naturally that source will be independent of temperature, because the number of defects in the solid will not change with temperature. So you get a temperature independent source of scattering from defects. Then there is a temperature dependent source, and that's the lattice vibrations, as I explained in the previous class, and that's seen very easily in experiment. The resistivity of a metal decreases practically linearly from room temperature down, but at very low temperatures it follows a slightly different behavior, and then it kind of saturates. I had shown this graph before. That saturation comes because all the ionic scattering due to the ionic vibrations have all died down, and then you have the prominent contribution due to the defects. At room temperatures, the defect contribution is still there, but it's very small compared to the contribution because of the lattice vibrations. We will study the modes of lattice vibrations or lattice dynamics in the coming classes. Now, let's now consider electron-electron scattering and understand an extraordinary and fascinating fact that influences the properties of solid. Now, suppose we consider this is the Fermi surface, the Fermi sphere, in 2 dimensions. It's a circle, the Fermi circle, and we're going to consider an electron scattering event. You consider 2 electrons. One electron is just outside the Fermi sphere, so it has got an energy E1 which is greater than EF. Then there's another electron 2 which is has an energy less than EF, so it is within the Fermi sphere. So we're going to consider the scattering event, these 2 electrons 1 plus 2 scattering to states 3 and 4. So state 1 is outside EF, state 2 is within EF, state 3 and 4 must be outside EF, because if I assume that all other states are filled and that there are no filled states, there are no empty states within EF, then the scattered states must be 3 and 4 must be outside the Fermi level. So E3 is greater than EF, E4 is greater than EF. So if I combine these two, I can now write this must be satisfied because of conservation of energy, and naturally because of E3 greater than EF and E4 greater than EF, this must be E1 plus E2 must be greater than 2EF. So now I can rewrite that as E1 minus EF plus E2 minus EF greater than 0. Subject to the constraints E1 greater than EF and E2 less than EF. Now suppose I consider this electron 1 to be just above EF, and that is a natural possibility, because at any given temperature, I had mentioned this in the class, you may have in previous classes, you may have also read this by now in your Stat Phi course, that in the Fermi-Dirac distribution, the Fermi-Dirac distribution is a step function at t equal to 0, and a very small portion of electrons from just below the Fermi level get excited to just above the Fermi level at room temperatures. Room temperature is still 2 orders of magnitude lower than the typical Fermi temperatures corresponding to the energy EF. So if I consider this electron 1 to be just above EF, then I can use this equation and these two constraints to show that E2 should be just below EF. If E1 is just above EF, E2 should be just below EF. You can easily see that from this constraint and this constraint. You can just pause the video, write it down and figure it out why that should be the case. You can give some numbers for you can set EF equal to 1, E1 equal to 1.2 and see what E2 is and so on, subject to those constraints. So if E1 is just above EF, E2 will be just below EF. Then in addition, momentum should also be conserved. So I can write this kind of an equation for the wave vectors. This is crystal momentum conservation, not total momentum conservation. Crystal momentum conservation. And this can be rewritten as k1 minus k3 should be equal to k2 minus k4, and those are the vectors. Those two vectors are shown here, and you can see that those two vectors should be the same. The length of these two lines, these two solid lines should be the same. And what that means is that the other two electrons, E3 and E4, should also be just above EF. So we started with E1 just above EF, and we the energy constraints made sure that E2 is just below EF. The momentum conservation constraint tells you that E3 and E4, the scattered states, should also be just about EF, just higher than EF. So it should be just closer than 2 EF. So all the scattering occurs in a band. So you can think of these two dark lines. You can just extend it all around the circle, and that's just a small band centered around EF, E equal to EF or K equal to KF. That's where all the action occurs. The rest of the electrons inside this Fermi sphere, they're all occupied and they're all dormant. So only in the small region outside that, in and out, just below and just above EF is where all the electronic scattering occurs. Now, the point is so if I consider this E1 minus EF as some energy difference delta, we had seen while calculating electronic or estimating electronic specific heats, we had said that the number of electronic states available are basically of that order, delta by KT. That's all, because the all other states are inside, they are dormant, they will not contribute, and because of the shape of the Fermi-Dirac distribution, the number of available states within this band about EF is only of that order. So it's you would think if you did not know about the Fermi-Dirac distribution, which comes from Pauli exclusion principle, if you did not know this, you will assume that all the electrons will be available for scattering. You know that in a solid there is a huge number of electrons available, right? The Avogadro number of electrons are available. The electronic density is also very large. We saw that in the initial videos. In spite of that, because of the Pauli exclusion principle, only a very small fraction of states just below EF and just above EF are available for scattering. So you can show that if sigma naught is the scattering cross section for all the electrons, if I assume all electrons are available for scattering, then the actual scattering cross section for electrons, that is electron scattering cross section that's actually observed in a solid, is basically delta by KT the whole squared into sigma naught. So it's a very, very small fraction. So compared to what will be the scattering cross section if all the electrons are available, the real scattering cross section, thanks to the Pauli exclusion principle, is a very small number, and one can show that it's like this scattering cross section is like something like 10 power minus 8 or 10 power minus 9 times lower than the scattering cross section due to defects, the scattering cross section due to lattice vibrations and so on. So in a solid, although there are three sources of scattering, one from defects, one from lattice vibrations, one from electrons, thanks to the Pauli exclusion principle, the electron scattering is extremely small. So the Pauli exclusion principle allows electrons in a solid to be treated as non-interacting particles in spite of high electron densities. That is the reason why the independent electron approximation is a very good approximation for many situations. Remember, there is something called free electron approximation, which assumes that the electron does not interact with the lattice. We have lifted that partially by saying the electron now interacts with a static lattice, but it has to be lifted fully by assuming that the lattice also has to vibrate. Then there is an independent electron approximation, which is this, where the electron is considered to the electron interactions are considered to be very small, and this is the reason why that that approximation is justified, because of the Pauli exclusion principle. The third approximation is called the relaxation time approximation, where we said, look, we don't care what the distribution of electrons are before it got scattered and what the distribution of electrons are, that is the Fermi-Dirac distribution after it got scattered and so on. Now we are going to talk more about that presently. So before we do that, one more interesting fact is that this slide you may remember from previous videos. This is the Fermi sphere at t equal to 0, and in the presence of an electric field or a force which accelerates the electrons, then the Fermi sphere will be displaced. All the electrons will get a delta k. There's a delta k momentum because of the force. We wrote an equation for that and so on. Now what happens if I remove the so at some time t, there is a force acting on the system. Now I am removing that force. Then this Fermi sphere should relax back to this equilibrium state. So when you consider that relaxation, so this is the displaced sphere, and this is how it will try to relax back. So you can have this state A will get scattered back to state B. This scattering occurs mainly because of defects and lattice vibrations. So the state A gets scattered to state B. If you see the wave vector distance from the origin, the length from the origin, this is the wave vector length Ka, and this is the wave vector Kb. So Ka and Kb are very different from each other. That means that there is inelastic scattering. Now for the Fermi sphere to relax back to, for a displaced Fermi sphere to relax back to its equilibrium position, there must be inelastic scattering. That inelastic scattering comes from defects and lattice vibrations. If you consider elastic scattering, for example, if I assume that this is distance Ka, if I assume that state A now goes to the state B here, so the wave vector Kb and Ka from the origin are the same, then you will notice that when the Fermi sphere tries to relax, it actually grows in size. You can see the Fermi sphere has tries to grow in size. That's the dotted line. That's not physical, because there is no external source to increase the energy of the electrons. You cannot inflate the Fermi sphere arbitrarily. So elastic scattering is unphysical. It doesn't. It does not explain relaxation to the equilibrium state. You need inelastic scattering for relaxation, and that happens, like I said, from lattice vibrations and defects. So now let's talk about what is known as the Boltzmann transport equation, and this is basically an equation or a mechanism to handle electronic transport without any of the simplistic assumptions that we have made before. But what we shall be doing is to derive the equation, and from this full equation we will make those simplistic assumptions one after the other and show that we can rederive the Drude equation, Drude model. So we now start with this expression for the Fermi-Dirac distribution. By now, when you are seeing this video, I am assuming that you would have studied this in the StatV course, so I am not going to derive this expression. This is the Fermi-Dirac distribution, and in the absence of any external field and under thermal equilibrium, that's what the distribution will look like. Now, in the presence of external fields, in principle, you expect the Fermi-Dirac distribution to change with position, change with wave vector and time. That's the most general way to project the problem. Now, this discussion I am following Solid State Physics, an Introduction to Principles of Materials by Hans and Hans Luth and Harald Ibach. It's usually called as Ibach and Luth. Now, now suppose we consider a displacement of the distribution from a time t minus dt to a time t. So you look at the system at t minus dt, and you apply the electric field, and then it has moved to another state at time t t, from t minus dt to t. So let's say the system has gone from at t minus dt, you can express the system in this form, the position in like this and the momentum like this. We have shown this in previous videos. You just need to look at it, and we are not going to look at any collisions for the moment. From this state, so from this position and this momentum position at t minus dt, in the presence of the electric field, the system evolves to r and k. You can, of course, if you reverse the problem from t to t plus dt, it will be the opposite. So I'm just following the discussion in the book, so that I just stuck to it. It doesn't matter. You can say you can go from t plus dt or t minus dt to t. Doesn't matter. So there is a change in the Fermi-Dirac distribution from f of r minus v dt k plus the impact of the force t minus dt to f of r, k and t. So how do you account for this? Now, in addition to this, in addition to just the change in the distribution, there must be some scattering mechanism. There must be some way in which the Fermi-Dirac distribution changes with time because of scattering, and I just add that term inside in this form and call it the scattering term. Now, to proceed, there are many ways to derive from this point. The simplest is to write down the expression for the total number of electrons. This is the total number of electrons, the expression for that in the whole solid. Obviously, this number will not change in time. We are not looking at situations where particles change. So the number of particles are fixed, therefore dn by dt is 0. This implies df by dt should be 0. So now if I do a total derivative expansion of f of r comma k comma t, then I get that. Then I club terms and I write this down. Now, in addition, we saw last class that the force can be written as h cross dk by dt. So I insert that in the equation and I get this. So I also written dr by dt as velocity. So now to this expression, we add another term, df by dt, and call it s. That's called the scattering term. That's a contribution. That's a contribution due to the scattering. So we assume that the scattering changes the Fermi distribution, and we don't know what the form is, but we are just going to add this there. So this is the full Boltzmann transport equation. And in the presence of an electric field, I can replace for f given by this, and all the terms on the left are usually called as drift terms, and this is the scattering term, that's the drift term. That's called the Boltzmann transport equation. Now I want to model what this term is, the scattering term is, and if I want to properly model it, then I need to look at the transition probability for the scattering. I need to consider occupied states, unoccupied states, and so on, and I'll get some kind of a very complex expression like this. Now this is very hard to solve, so we are not going to bother with this full expression now. But the most easiest way to model the scattering term is to write down a rate equation like this. This is the mathematical expression of the relaxation time approximation. This just means that the Fermi-Dirac distribution exponentially decays to f naught. So if I assume that f naught is the equilibrium Fermi-Dirac distribution, f of k is the distribution when there is an external perturbation, whether it's a magnetic field, thermal gradient, or electric field, f of k. If I switch off the external field, f of k decays exponentially to f naught of k. It reaches f naught of k exponentially with a time constant given by the relaxation time tau of k. That's called the relaxation time approximation. So now I'll go back to this to the Boltzmann equation. I will also get rid of this term del R of f. I will assume that the Fermi-Dirac distribution does not change with space. So I'll get rid of this, and I will also write down this expression in the stationary state. So I'll get rid of this as well. I'll write for when this is 0, the Fermi-Dirac distribution under the relaxation time approximation, that's the relaxation time approximation is introduced, is given by this, which can be written like that. And that's called the linearized Boltzmann equation. The reason why it's called the linearized equation is the full expression. If you look at this, you have f here and you f here. You have to solve this expression iteratively. So you have to choose some form of f, then you have to put it in the expression, calculate this, find out the deviation, put that form of f again. So you have to iteratively solve this, and when you iteratively solve this, you will get f as a function of several powers of the electric field. Whereas if you use the relaxation time approximation, you guarantee that it's linear. F just depends on E and not E squared, E cubed, and so on. Now coming to electrical conduction in metals, in the previous video we saw that we could write the thermal current density as this, the electrical current density as this. Now in this expression I have not included the occupation probability of the electrons, that is the Fermi-Dirac distribution. That is because these expressions were done at t equal to 0, although I probably failed to explicitly mention this. F equal to 1 at t equal to 0. So when I do the compute this at t equal to 0, I don't need to include the f in the integral because f is equal to 1. It will drop out automatically. But if I do it generally at any given temperature, then f also must be included along with the dn, ev, and here also for the thermal current. For this is the expression for the electrical current, this is the expression for the thermal current with the Fermi-Dirac distribution included, because the Fermi-Dirac distribution tells you the occupation probability for any given energy level. So I need to include that when I integrate. So now that's the expression with the linearized Boltzmann equation put inside. So now that's the full expression for the electrical current. So I replace for f of k the linearized form of the Boltzmann transport equation, which is this form, and I put it there. Now we again make several simplifying assumptions. We will assume that we'll assume a simple cubic lattice. It's isotropic everywhere. So we will also so if the current is up, if the electric field is applied in the ex direction, the velocity will also be in the vx direction only. There will be no components along Vy or Vz. Those things are possible, but we will assume that there is no current in the Jy and Jz directions, because the current will only be in the Jx direction, because we are applying the electric field in an isotropic simple cubic lattice in the x direction. Then this df0 by dkx can be shifted with the in terms of the energy integral, and I'll write this, and the dE by dk can be expressed in terms of the velocity vx. So that can be put in there. Then there is this then there is this vx. So this v of k will now become vx of k. Then the integral vx of k f0 will vanish when I integrate this. So this integration is done over the entire first primitive cell, because that contains all the k vectors. We saw this in the last class. This is because f0 is a even function, and within the first Brillouin zone, Vx is an odd function. We saw that for a one-dimensional case, simple one-dimensional case, but that's true for all dimensions. So this, so I'm integrating basically over an odd function, and that integral will vanish. So this term v of k into f0 will vanish, and so if I put that all inside, then I'll get this expression. So I've replaced df by dkx in terms of this. I've done all the substitutions. Please do this step by step by pausing the video, then only you will understand. That's the current density. Now I can write I can replace the jx by simply the conductivity by following this, and I get that. Now I have this guy here. This is the derivative of the equilibrium Fermi-Dirac distribution with respect to energy. If you do the derivative, if that's the Fermi-Dirac distribution at some temperature T, which is much smaller than the Fermi temperature. That's where it's almost a step function, just a very small amount of electrons here have gone out there. So if I take this derivative, I will get this kind of an inverted sharp function, and I can assume that as long as I stay well below the Fermi temperature, that is at room temperature is fine enough, then I can replace this by a negative delta function. That is, it just is inverted, so I can replace it by a delta function of this form. And also this means that all the energies will just be within a small shell of EF. I can basically assume that I am doing the integral over EF. So the integral can be thought of as confined to a surface of constant energy, and I can now change the change variables from dk. So I can write this. So I have this surface of constant energy. I have this vector k perpendicular. That perpendicular will be parallel to the gradient of the energy del k of E, and I can write dk perpendicular as dE divided by mod of del E. So I basically change variables and I write dk is equal to the dFE. So dFE is basically this area element on the constant energy surface. So the area element times the dk perpendicular, and I can replace for dk perpendicular from here, and I'll be able to get this. This is just basic vector calculus that you must have studied in earlier classes. So please recall those and appreciate what's happening. So I can now change variables from dk to dFE into dE by this, and I can substitute this in terms of the velocity. This grad E I can substitute in terms of the velocity, and that's what I'll get. So I insert that into the integral, and that's what I get. Now we can make, so now there is a delta function sitting here. I can apply the delta function, and that will get rid of the integral over dE, and I'll be left with this. Now I make further additional approximations. Now I assume that I just need to worry about the integration is over EF, so I only need to worry about the relaxation time at the Fermi level, the velocity at the Fermi level, and then there is this Vx squared. I assume it's an isotropic solid. So just like what we did in the expression for thermal conductivity, I replace this Vx squared by the average of the velocity, the entire velocity V squared, but that's 1/3, because V squared average will be Vx squared plus Vy squared plus Vz squared. All of them are equal, so I can write Vx squared is 1/3 of the average of V squared at that Fermi level EF, just like what we did in the thermal conductivity calculation. So I put that all inside here, and that's what I'll get. Now I'll just get a surface integral which is done at E equal to EF. So if I assume it's a spherical Fermi surface, then it's basically a surface integral, and I'll just get the area of the basically the area of the sphere as that 4 pi kf squared. Now Vf, the velocity, can be written in terms of kf in this. M star, I've written it strictly because it's an electron on a band, so instead of the mass m, I have to take the effective mass, so I've just put m star there. And kf cubed can be shown to be equal to 3 pi squared n, where n is the number of electrons per unit volume. Please show this. Use the calculation for the number of states available in a volume dk or whatever, the density of states calculation. Use this, use the density of states discussion and compute this. Kf cubed is equal to this, so I put both of them inside, and I'll now get this expression for sigma, which will simplify to this. Now you can see that's just the Drude model. Now from the Boltzmann transport equation, through a myriad of approximations, so many approximations, we are now able to get the Drude form. But the Drude form, the conductivity now, the expression now tells you that you only need to worry about the relaxation time at the Fermi level, because all the action occurs only at the Fermi level. The only excitable electrons are available close to the Fermi level. So you just need to worry about the relaxation time at the Fermi level, and you are able to get the classical Drude result. Of course, Drude did not know all this. He just assumed all the electrons were participating in the conduction and so on, in the scattering and causing further resistivity and so on. But we now know only the electrons close to the Fermi level are responsible for scattering. And if I want to find out the temperature dependence of conductivity, then I need to only worry about the temperature dependence of this relaxation time. So the entire effect of the lattice vibration sits inside the relaxation time, or how the relaxation time changes with temperature. That is the subject that's a little too advanced for this course. You may have to read it in elsewhere, or if you want to do research on this topic, then you definitely need to learn more about it. So that's all about the Boltzmann transport equation and how it gives you the Drude model under simplifying assumptions.